This is the solution video for question 28 from part B of the 2019 ECAA paper. In this question, we're asked to find a range of k such that this equation, x minus 2 cubed minus 12x minus 2 plus k squared is equal to 0, has exactly one real root. I'm given 8 different options for the range of k such that this all holds. The key to this question is look at it graphically, because it's very hard to do purely algebraically. It really helps to have a picture to imagine what's going on here. So what will this graph look like? So we know if we have y equals x minus 2 cubed minus 12x minus 2 plus k squared, we've got a positive coefficient of x cubed if we expand this out, so we know it's going to look something like this. We've drawn it with 2 turning points. We don't necessarily know has 2 turning points yet. It could have like an inflection point instead, but generally this is what it looks like. And what we're looking for, well, let's mark the turning points of the graph. We want exactly one real root, so this wouldn't do at the minute because this has 3 real roots. So for one real root, what do we need? Well, if we move the graph around a bit, we see what we need is one of 2 scenarios. We either need the 2 turning points to have positive y coordinates, and then we hit the x-axis only once here, or conversely, we need both turning points to be less than 0, because then we have only one root here. So in either case, what this has revealed is the key to this question is work out where the turning points are and the coordinates of the turning points. And given we've got a cubic here, that probably should be doable. So let's find these turning points. So at the turning point, we know the derivative of x minus 2 cubed minus 12x minus 2 plus k squared needs to be 0. So differentiating that, we have 3x minus 2 squared minus 12, and then the rest of this disappears, equal to 0. So we need to expand this, so we'll get 3x squared minus 12x, because so we get minus 4x from expanding the bracket times 3. Then we also get minus 2 squared, which is plus 4, times 3, which is plus 12, but we have this minus 12 here, so that cancels. So 3x squared minus 12x is 0, which factorises as 3x times x minus 4 is 0. Which is excellent, because we know our turning points will have x coordinate 0 and x coordinate 4. But the thing we really care about is what the y coordinates are. So, turning points. So, 0, we just need to sub 0 into here to get the y coordinate, so minus 2 cubed minus 12 times minus 2 plus k squared. And similarly for 4. And let's tidy these up. So we get 16, because we get minus 2 cubed, which is minus 8, minus 12 times minus 2, so minus 8 plus 24, which is 16, plus the k squared. And here we've got the k squared plus 8 minus 24, so 4 k squared minus 16. And these are our turning points. So what does this tell us about our graph? Well, we need to update our graph. So we know we have 2 turning points, so we know we've got roughly the right shape. And we know that for us x equals 0, 16 plus k squared is always going to be greater than 0. So we know this point is going to be somewhere around here. What we don't know, however, is if our other point is less than 0 or greater than 0. Because this could take either sign depending on k. But we know we want it something like this scenario, where k squared minus 16 is greater than 0, because then we have one root here. So this is the last criterion, the only criterion we need, k squared minus 16 greater than 0, because that tells us if the y coordinate of this is greater than 0. So this is the same as k squared greater than 16, which we can solve quite easily, because it means k is bigger than 4, or k is less than minus 4, and that corresponds to option A in our multiple choice, and so we know our answer is A.